Newton-Raphson method to calculate this nonlinear algebraic equation at every xi plus 1, okay, to get the value of yi plus 1. That means we need to call this Newton-Raphson method for every step of the way, okay. So that is one way to go about this thing, but fortunately there is a kind of a easier solution that exists. So instead of going for a Newton-Raphson method, of course, Newton-Raphson method is going to give you the same answer as what we are going to see now. So in this method, we're going to avoid this iteration. We're going to avoid iterations by going for linearization. Okay, linearization of the RHS term. Okay, so what we're going to do is essentially we have f of xi plus 1 comma yi plus 1, which is basically a nonlinear function. Okay, as we said, now we want to linearize this thing. So we want to linearize, but then in the values of xi plus 1, yi plus 1, the difficulty is that xi plus 1 is not difficult. This is basically we already know because we are going from some xi to xi plus 1. This is basically an increment of h. So xi plus 1 is already known. The only difficulty is with yi plus 1. We don't know what is the value of the function at xi plus 1, right? This is the main difficulty because yi plus 1 is not known. So this is what is unknown. So we have to now linearize this f of xi plus 1 yi plus 1, not about xi plus 1, rather about yi. Okay, that means we want to because f xi plus 1 yi plus 1 is in general nonlinear. Okay, what would happen if this were just linear instead of nonlinear? If this was linear, then it is much easier, right? Because yi plus 1 comes out as simply as some yi plus 1 term, and that yi plus 1 can be taken to the left hand side and then added to this value, and then you could basically just solve it because it is now a linear equation. Okay, but then the difficulty is that f of xi plus 1 yi plus 1 is in general a nonlinear function. That means yi plus 1 could be appearing as yi plus 1 square or some sign of yi plus 1 or some e to the power of minus yi plus 1 and so on. It's basically is a nonlinear function. As a result, you won't be able to combine with this yi, right? So when you put these together, you are getting a general nonlinear algebraic equation. So is in general because f of xi plus 1 yi plus 1 is in general nonlinear, and yi plus 1 is the unknown value. Okay, let us linearize this. Linearize f of xi plus 1 yi plus 1 about which point? About xi plus 1 comma yi. Okay, so we wrote this because we already know what is xi plus 1. Xi plus 1 is just the next grid point value, which we already know. Only is that we don't know yi plus 1. That's why we are normalizing about yi plus 1. Okay, that means if I use the Taylor series expansion for f of xi plus 1 yi plus 1 about f of xi plus 1 yi, this is going to be f of xi plus 1 yi plus yi plus 1 minus yi times partial f by partial x at partial f by partial y at I plus and so on, right? That is what we have. Yeah, so this is what we have. So then what we can do is that because f function is known, I can also calculate what is partial f by partial y at I, right? This can be calculated. So if this is the case, we can go back and substitute for this expression into the implicit Euler expression, that is, which I'm going to repeat here. So the implicit Euler is yi plus 1 equals yi plus h times f of xi plus 1 yi plus 1. So we're going to substitute for f of xi plus 1 yi plus 1 from here, which is going to give me yi plus 1 equals yi plus h times f of xi plus 1 yi plus yi plus 1 minus yi times partial f by partial y at I. Okay, and then of course there are higher order terms which we are neglecting. Okay, so neglecting the higher order terms. Okay, any questions on this, on what I have just written? Is it clear, or does it sound not clear?
Clear, sir.
Yeah, okay, fine. So if this is the case, then I can now bring terms to one side. So I can write this as, for example, yi plus 1 partial f partial y. I can bring it to left hand side. This is going to be yi plus 1 times this is 1 minus h times partial f by partial y I, right? This h is being multiplied, equals on the right hand side we have yi times 1 minus h times partial f by partial y at I plus h times f of xi plus 1 yi, right? That's what I have. That means I can calculate what is yi plus 1 equals yi plus, okay, h times f of xi plus 1 yi divided by 1 minus h times partial f by partial y at I. Okay, so that is the expression I have, which is basically a linearized form of implicit Euler method. Okay, so that is the implicit linearized form of the implicit Euler method. So this can be used instead of this expression, which is basically has a nonlinear function. Now, of course, if you use this particular linearized form, or if you use this nonlinear form, eventually both of them should converge to the same answer. Okay. Now, if you have to do this thing, then you have to implement. Then you don't need a linearized form as this thing. But then, however, once you substitute, you would get this nonlinear algebraic equation, which you can solve it with using a Newton-Raphson method. Okay, at every xi plus 1, xi plus 2, and so on, and then calculate it. So that is going to give you the same answer as what you would get from here, from the linearized form of the implicit Euler method. Okay, so the implicit Euler method is also formally, or is also locally second order accurate. Second order, that means order h square, and globally is going to be order h, similar to the explicit Euler method. And then, of course, the implicit Euler method is much more stable than the explicit Euler method, because we are bringing in information from the next time step, from the unknown time step. However, the method is only order h. So, so as a result, this is somewhat used, the implicit Euler method, rather than so it is not going to diverge as much as the the explicit Euler method as such. Okay, fine. So that's about the implicit Euler method. Let us move on to the trapezoidal method. So let us move on to the trapezoidal method. So what we have is basically dy dx equals f of xy. So this is the first order initial value problem that we are trying to solve. And if I were to look at this integration analytically, then essentially we want to solve this from some yi to yi plus 1. We want to integrate this equals integrated from xi to xi plus 1. Sorry. yi to yi plus 1 equals integral xi to xi plus 1 f of xy dx, right? I just brought this dx to the right hand side and then integrated both sides from xi to xi plus 1 and yi to yi plus 1. So what we have here is that integral dy is y, so that means yi plus 1 minus yi equals, on the right hand side what we have is integral xi to xi plus 1 f of xy dx, right? So what we have done till now is that if this entire integral was evaluated at xi, if it is evaluated at xi, and then we multiply with the dx, that is xi plus 1 minus xi, That was our explicit Euler. If the entire integral was evaluated xi plus 1, yi plus 1, and then multiplied with xi plus 1 minus xi, that is h, that was your implicit Euler. Whereas in the trapezoidal method, we're going to integrate this xi to xi plus 1 f of xy dx using the trapezoidal rule. Okay, what was the trapezoidal rule? Trapezoidal rule is if you have, let us say, some function. Let us say we have some function. Then, if you know what is the value of this function at xi, and then xi plus 1, then essentially you're going to draw a line, this one, and then the area within that is going to be approximated as the area supposedly under this curve, right? Essentially, we are of course making some error, right? This is the this gap is the error we are making, but then that is an approximation. So that means we want to write this as this is the area of the trapezium, right? So that is going to be xi plus 1 minus xi divided by 2, that is this distance divided by 2, times f of xi by I, that is this value, plus f of xi plus 1 yi plus 1, right? That is this value. That means this value plus this value by 2 times this width, okay? That is basically your area under this trapezium. So that is the value of the integration. And then we already know that xi plus 1 minus xi is nothing but h. That is the distance we have times f of xi yi plus f of xi plus 1 yi plus 1. Okay, so that's the integration value. So if I go back and substitute into this formula, so what we get is yi plus 1 minus yi. So if I take this yi to the right hand side, we're going to get yi plus 1 equals yi plus h by 2 times f of xi yi plus f of xi plus 1 yi plus 1. Okay. Now again, what you see is that the trapezoidal method is also an implicit method. It's also an implicit method. Okay, it is also an implicit method, and also the f of xi plus 1 yi plus 1 is in general nonlinear. So, so we cannot directly solve for this. Either we have to employ some kind of an iterative method. Otherwise, we have to linearize it. Okay, so that is what we have to do. Again, you can probably draw a similarity of this trapezoidal method to another method that we have already learned. So the trapezoidal method in the context of ordinary differential equations is similar to the dash method in the solution of certain type of partial differential equations. Okay, and this type of partial differential equations happen to be kind of a parabolic type of partial differential equations. So my question is, what is this counterpart of this method in the solution of partial differential equations that we have already seen? To which method do you relate this trapezoidal method in the context of solution of PDEs? So we have looked at this in the basics of finite difference method in the, when we are trying to solve the one-dimensional transient heat conduction problem. What was this method looks like? You remember from the previous classes, in the context of solution of PDE, there is a method which is exactly like this, where we have done similar kind of splitting or expression. You recall, maybe you can recall that as the Crank-Nicolson method. Okay, so Crank-Nicolson method in the solution of PDEs is nothing but trapezoidal method in the context of ODEs. Okay, so there also you remember we had half of these two because on the right hand side, if things were evaluated at half of n plus 1 and n, on the left hand side things were evaluated at about n plus half. That's why we went from ui n plus 1 minus ui n divided by delta t, that is about n plus half. Okay, that's what we have done. So this is the same. Of course, we have not established the order of accuracy, but then we will establish this little later. So the trapezoidal method, for now we are going to just write it. The trapezoidal method is locally order h cube in order h cube accurate. And globally, it is going to be order h square, okay, with the same logic as we discussed yesterday, because we're going to do h cube order of accuracy for per step, that is locally. But then when you do over several steps, you have to multiply that with so many, so n times, but then n is nothing but L by h. So which is going to give you only L times h square. So that is basically order h square accuracy globally, okay. So then again, we are bombarded with the same problem that the resulting equation is going to be a nonlinear algebraic equation. Now, how do we solve this problem? So again, we have to go back and kind of linearize it. Now, what we see is that essentially, because this is order h cube accurate, like this is basically order h cube accurate. We have not established that one, how it is yet. But then because it is order h cube, it doesn't make sense to solve this equation to any higher order accuracy, okay, or to machine precision. So, because the trapezoidal method is only order h cube accurate, we don't need to solve the equation exactly or to machine precision, right? So that is whatever the computer's precision. We don't have to solve it exactly. Rather, if we are able to solve a linearized problem with the same order of accuracy, then we are good, right? We don't have to worry about the accuracy but then we will be able to benefit from this procedure because now we have made a linearized version of the problem instead of the nonlinear problem we have. So as a result, we don't have to do this Newton-Raphson method or any other iterative technique to solve for a nonlinear algebraic equation at every step of xi plus 1 and so on. Okay, so that means we're going to follow the same principle. We're going to now linearize this f of xi plus 1 yi plus 1 about f of xi plus 1 and yi. Okay, so we're going to linearize f of xi plus 1 yi plus 1. So linearize about xi plus 1 and yi. Okay, so that's going to give me f of xi plus 1 yi plus 1 equals f of xi plus 1 yi plus we get yi plus 1 minus yi. See here we're getting yi plus 1 minus yi. We're not getting h here, right? The h is supposed to be xi plus 1 minus xi, but then we are not linearizing about xi plus 1. We are leaving xi plus 1 as it is. So that is why we're getting yi plus 1 minus yi. And then this is going to be partial f by partial y, because this is yi plus 1 minus yi about I plus yi plus 1 minus yi whole square by 2 factorial dou square f by dou y square about I and so on. Okay, so that's what we have. Now how many terms do we have to include in this to approximate f of xi plus 1 yi plus 1? So if you go back or we realize that essentially yi plus 1 minus yi, right? This term is order h, right? If you have to expand yi plus 1 about yi, you're going to write yi plus 1 equals yi plus h times dou y by dou x and so on. So that means approximating yi plus 1 about yi is order h accurate. So that means this term is still here is order h accuracy. But then if you go back, if this was expressed to order h accuracy, there is a multiplication with h here. So there is a multiplication with h here. So as a result, this term is going to be eventually order h times order h. This is order h square. And That means we are, okay, this is going to be order h square. That is not good. Okay, so this is going to be order h. So should we go for the second term? No, this is already order h, right? Then we are not going to, because this is order h cube is what we want. F of xi plus 1 y plus 1. Where would I get the, this is order h. I don't need to go for here because this is going to basically make it order h cube. Would it conflict with what I have? Let us see. Okay, so I have h by 2 plus f of xi yi plus f of xi plus 1 yi plus 1. Okay, so this term is, if I can express to order h square. Oh, okay. So I'm going to include this term, right? So I'm going to include this term. This is order h, but then this term is order h square. So the truncation error which I'm not going to write is of the order h square, right? So this term is order h square, which I'm truncating. That means I'm only including up to here. That means my truncation error is order h square. So when I plug it in here, the truncation error is order h square. When multiplied with h, it's going to give me order h cube. Okay. And that is not going to make this any lower because it is already order h cube, and I'm only making some more truncation error of the same order, right? So then this is also going to be order h cube. As a result, I am okay expressing f of xi plus 1 by I plus 1 to include the first two terms. I don't know. Is it clear what I'm trying to say? So the thing here is that we want to convert this nonlinear function into a linear function, okay, into a linearized function. But then while doing so, when we have expanded f of xi plus 1 by I plus 1 about the Taylor series about f of xi plus 1 by I, we noted that we have several terms. We have the we have first term, second term, and third term. But then how many terms should I include? What I'm saying here is that we just need to include the first two terms, because after this is going to be order h square, because yi plus 1 minus yi is order h. So as a result, this is order h square. Okay, so that is the truncation error. If I include up till here, the truncation error I'm making is order h square. That order h square, when you put in here, will be multiplied with this h by 2, right? Is multiplied with h by 2, which is basically order h square times h is order h cube. So that is going to be about the same as the already existing truncation error we have in this particular method. Okay. So as a result, I'm not changing the order of accuracy of the method. I'm only going to linearize the problem, okay, by including two terms from there, just like what we have done in the case of implicit Euler method. Okay, so I'm going to substitute for these two terms instead of f of xi plus 1 yi plus 1 back into the equation. My equation for trapezoidal method was yi plus 1 equals yi plus h by 2 times f of xi yi plus f of xi plus 1 yi plus 1. Okay, that's what I have. Fine. Then if this is the case, I have yi plus h by 2 f of xi yi plus, I'm going to write this as, for this, I'm going to write this as f of xi plus 1 yi plus yi plus 1 minus yi times partial f by partial y at I. Okay. And then this is still order h cube even after this substitution. Okay, so that's what I have. Then I can write this as just like the way I have done before. I'm going to bring yi plus 1 terms to left hand side. So that's going to basically make it yi plus 1 minus h by 2 partial f by partial y at I equals yi plus h by 2 times f of xi yi. Then I have minus h by 2 partial f by partial y I times yi. Okay, so that's what we have. So I don't need these brackets. Okay, so that is what I have. That means on the right hand side also I can write yi times 1 minus h by 2 partial f by partial y at I. Okay, plus h by 2 times f of xi yi. Okay, is it correct? Did I miss something? So that means yi plus 1 equal to, I can divide with this thing, which is basically the same as this. So I can write this as yi plus h by 2 f of xi yi divided by, oh, sorry, not f of xi yi. This is, I think I made a mistake here. So yeah, this is correct. F of xi yi divided by 1 minus h by 2 partial f by partial y at I. Okay. So that's what I have. Okay. So that is the linearized trapezoidal method, which doesn't require iterations to calculate yi plus 1. Okay. Fine. So that's about the trapezoidal method. Any questions? Is why we are doing linearization clear here in this context?
Yes, sir. Like, but in the
Hmm.
exam, like how the questions will be there. Like, suppose if you're expecting a problem in this.
Sure. So I'll do an example problem now. Okay. For example, let us say we will work out a problem. Let me take this example. The differential equation is, let us say, dx by dt equals 1 plus x squared plus t cubed. Okay, that is what we are given. And then the initial condition is given, x of 1 equals minus 4. Okay. Let us say take delta t to be equal to 0.01. And then, okay, so we will not, I will not ask you to calculate all the way to x of 2, but then the question says you calculate all the way to x of 2, which is, okay, which is too much in this case with hand calculation, but maybe we'll go for 5 steps, because if you want to go to x of 2, then essentially this is 1 by 0.01, which is going to be 100 steps, right? So which is too much. So we will probably do 5 steps or something. I'll probably ask you to, let us say, calculate up to x of 1.05 or something, 4 or 5 steps or something like that. Okay. So this is the ordinary differential equation that is given. Basically, this is the initial value problem we are given. And then we are asked to evaluate, let us say, using explicit Euler method, explicit Euler, implicit Euler, and then the Taylor series method, and then let us say using the trapezoidal method. Okay. We will try to do some numbers here. I may not be able to calculate all the numbers, but if you have a calculator handy with you, you can calculate and tell me. So, okay, let us try to do this problem using explicit Euler method. Okay, now what you see here is that this is slightly different from the governing equation we have been studying. We were looking at dy dx equals f of xy. So here the independent variable is t is the independent variable, and the dependent variable is x. Okay, till now we have been looking at independent variable x and then dependent variable y. Okay, so except for that, this is very much the same as what we have been studying. Okay, then let us look at explicit Euler method. So in the explicit Euler method, we will calculate the new value of the dependent variable xi plus 1 equals xi plus delta t times f of xi ti, right? Or f of ti xi. Okay, so explicit Euler is the easiest because you can just have to substitute and then calculate. So we are starting from I equals, so x of I is 1. So we want to calculate what is x value at, so I is, x of I is basically 1. That is what we are given. X of I equals 1, or x of 0 is 1. And then we want to calculate what is x of I plus 1, that is delta t, right? Or we can write this as, I can write this as x of I equals 1, x of I plus 1 equals 1.01. Okay. Sorry, that's not 1.01. So x of, so the ti equals 1, and we have to calculate ti plus 1 equals 1.01. Okay. But then x of I at ti, that is x of I, is given as minus 4. we need to calculate what is xi plus 1. Okay, that is the question. Of course, and then we have to repeat the process. So here it is easy because f of ti xi is nothing but what is there on the right hand side. So I just need to write this as 1 plus xi square plus ti cube and then substitute into this formula. So I can calculate what is xi plus 1. That is the value of the dependent variable equals x of I, or this is nothing but x of 1. Okay, so I want to calculate what is x at 1.01, that is t plus delta t. X of 1 plus delta t is 0.01 times f of ti xi is 1 plus x I square plus t cube, right? So it is basically t is now ti is basically 1 cube, right? That is what we are given the initial condition. Okay, so what is x of 1? X of 1 is given as -4. So this value is going to be -4 plus 0.01 times 1 plus 1 coming from here, and then we have plus 16, right? This is x of 1 is -4, this is 16. So you can calculate what is x of 1.01 as this quantity. Okay, that's going to be -4 plus 18 times this one. That is going to be 0.18. This will be some minus 3.82 or something. Okay. Okay, so that is the value we got. And then, of course, I can now calculate what is x of 1.02 equals x of 1.01 plus delta t 0.01 times 1 plus x of 1.01 square plus 1.01 t cube. Okay, that's what we have. That means x of 1.01 is minus 0.38 plus 0.01 times 1 plus minus 3.82 square plus 1.01 cube. So if you simplify, you're going to get what is x of 1.02. Okay, that is how your explicit Euler method is going to work. Now, of course, you have to repeat this 100 times to get to x of 2. Of course, this is not a nice suitable problem for hand calculation. Of course, if you want to do a couple of iterations to show, that is fine, but then we will not wish to do this hand calculation one by one. Rather, it is a very good candidate for writing a small program in MATLAB where we can just plug in what is the delta t, what is the function, and then it will just calculate using explicit Euler method. It will give us what is x of 2. Okay, so that is how you could do with explicit Euler method. Is it fine? You know, so you can expect these kind of problems in the assignment or in the assessment. Okay, is it fine? Did I make any mistakes?
So,
you can correct me.
Sir. Yeah, this is helpful, sir. Yeah, sure. Thank you, sir.
Yeah, so you're able to do this thing. Okay, so we'll do like this. Now let us try to do what is implicit Euler method. So implicit Euler method. Okay, I think now I'll show you the nonlinearization we are talking about. Implicit Euler method is, okay, we are again given what is this problem, dx dt equals 1 plus x square plus t cube, right? Yeah, 1 plus x square plus t cube. Then implicit Euler method. What is the expression? Yi plus 1 equals yi plus h times f of xi plus 1, yi plus 1, right? That means I'm writing instead of xy, I'm writing in terms of x and t. So this is going to be xi plus 1 equals xi plus delta t times f, that is 1 plus xi plus 1 square plus ti plus 1 cube, right? Because everything is evaluated xi plus 1, yi plus 1 in the function, right? Because this is f of xi plus 1, yi plus 1 in the original formulation. Okay, so in this case, it happens to be f of ti plus 1, xi plus 1. Fine. Now, if this is the case, you can clearly see what I have is, I have xi plus 1 minus delta t xi plus 1 square equals xi plus delta t times ti plus 1 cube, right? So now everything on the right hand side is known. So let us say this will come out to be some value, some 2.53, whatever. I'm just writing something. On the left hand side, you see that xi plus 1 is our unknown. That means if I were to write that as some variable, some xi plus 1 minus delta t xi plus 1 square equals this thing. Okay. Now, in this case, this happens to be easy quadratic equation, right? which you can solve using a calculator as such. Okay, but in general, this may not be, but then still, this is a nonlinear equation. This is not a linear equation because this is quadratic equation. And you don't have just xi plus 1 on the left hand side. You have xi and then xi plus 1 square. Okay, so so in general, this will be a nonlinear equation. So we will use the method that we have developed in the implicit Euler method, which is basically the linearized version of this thing. Or I can again try to calculate the same thing from this, from this formula instead of using that method and see if that is the same. Or even I can directly put the same method. Okay, so let me go back and put that method. What was the linearized version? Linearized version was for the implicit Euler. We have yi plus 1 equals yi plus h times f of xi plus 1 yi divided by 1 minus h times dou f dou y. Okay. Okay. So what we have is then the linear version we have is xi plus 1 equals xi plus h is delta times f of pi plus 1 xi divided by 1 minus h times dou f by dou x at I. Okay, so that is the formula which we have in terms of x and t. Okay, so then we can apply this formula. This is going to be xi plus 1 equals xi plus delta t times f of ti plus 1 xi. That is going to be, this is the f function. So I have to write this for ti and xi plus 1. Okay, that means this is going to be 1 plus, this is going to be 1 plus xi square plus ti plus 1 cube divided by 1 minus delta t. What is partial f partial x? Partial f partial x. Yeah, this is with respect to the independent variable. So, sorry, dependent variable. So f is 1 plus x square plus t cube, right? That's what I have. Okay. Then what would be partial f partial x? That is differentiating with respect to x. Everything else is a constant. So this is 2x. Okay. So that means minus delta t times 2x. Okay. That's what we have. So this is the expression. I can also, yeah. So this is the expression. Now in this, you see that there are no nonlinearities. Xi square is known. So that means I can write my xi plus 1, which is x of 1.01 equals x of 1, which is minus 4 plus 0.01 is the delta t times 1 plus minus 4 square plus 1.01 cube divided by 1 minus 2 times, this is xi, okay, minus 2 times minus 4 times 0.01, okay. So this is going to be minus 4 plus this quantity. What will it come out to be? Can somebody calculate and tell me? I have my calculator here. I'm going to just grab it. Okay, so what is this value? This is 17 plus 1.01 cube. If anybody has an answer, please tell me. Otherwise, I'm going to just calculate in a bit. So you have 1 plus, this is going to be denominator is simply 1.08. Right. Yeah,
It's
plus.
It's 2.0034.
Oh, 2.0034, huh?
No. Okay, minus 4. Okay.
Minus 4.
Minus 1.9966.
9966. Okay.
Yeah.
So as you can see, already the answer is quite different from what we got from the previous value, right? Earlier we got minus 3 point something. This is almost half of that. You can see that there is a difference in the value. Okay. Okay. Fine. So I think that is because of the, the stability of the implicit Euler method, maybe. We have to see which is correct. Okay, we will verify that later. But this is the, in general, the approach to solving. I hope I have not made a mistake in converting or writing the linearized form. Hopefully this is correct. You can verify if you have your notes handy. Okay. Fine. So, but then of course you can now proceed. You can write what is x of 1.02 in terms of x of 1.01 and so on. Okay, so everything else has to be in terms of x of 1.01 and then ti plus 1 will become Ti plus 2. That means it will become 1.02 cube and so on. Okay. So that is how we can proceed. And then, of course, this also can be easily coded up. Fine. Okay. So that is about the implicit Euler method. Let us see if we can try to do it with the Taylor series approach. Taylor series method is going to be a little more involved because we are given dx by dt equals 1 plus x square plus t cube x of 1 equals minus 4. Taylor series method is xi plus 1 equals xi plus delta t partial x partial t, which I'm writing it as x prime at I plus delta t square by 2 factorial x double prime at I plus delta t cube by 3 factorial xi triple and so on. Okay, so that is the method. So depending on how many terms we wish to include, we can keep going. Okay, if we say include up to 1, 2, 3, 4 terms, we can calculate up to here. Or if it says include up to 5 terms in the Taylor series expansion, we can use the 5th term and so on. Okay, but then now we know what is on the right hand side. Okay, so this is did I write it correctly? Xi plus 1 equals xi plus yeah. So, but then we know that x prime is nothing but dx dt. Okay, that is equal to 1 plus x square plus t cube. So this can be evaluated at ith location because we want it for I. That means this can be evaluated x prime of I is nothing but x prime at 1. That is nothing but 1 plus x of minus 1 square plus 1.01 cube. Okay, so that is the first value. What about x double prime? That is d square x by dt square. That means it's going to be d by dt of 1 plus x square plus t cube. That is nothing but d by dt of 1 is 0. D by dt of x square is 2x x prime plus t cube is going to be 3t square. Okay, so this we need to evaluate at x I double prime. That means substitute for t equals 1 and then x equals x of 1. That means minus 4. Okay, and then that can be calculated. Similarly, x triple prime is going to be d cube x by dt cube. That is going to be d by dt of this quantity, right? D square x by dt square. That is nothing but d by dt of 2x x prime plus dt square, which is going to be nothing but there will be 2 terms from here. That's going to be 2 times x prime square plus 2 times x double prime plus 6t. Okay, so that is x triple prime, and then x triple prime can be evaluated at I. That is nothing but 2 times x of 1. X prime square. So you need to put what is the x prime value you got here, square of that. Okay. I'm not writing this thing. So you can evaluate what is x triple prime of I. And then similarly, x of 1, x double prime of 1, which you would get here. And then t is going to be 1. Okay, so you can plug in all those values. So once you have all these values calculated from what we discussed, yeah, go ahead. Question? So once you have all these values, you can put delta t value and then update what is xi plus 1. Okay, so xi plus 1 you can calculate, that is x of 1.01 will be sum of all these 4 terms that we would obtain. That would be x of 1.01. Again, this can be easily coded up because this is like more general case of an explicit Euler method. Instead of just 2 terms, we have 4 terms or 5 terms, whatever is the number of terms that are given. In this case, fortunately, the function is kind of smooth enough that its higher order derivatives exist. So it kind of keeps giving you non-zero derivatives, okay, as you go. And of course, once you have x of 1.01, you can calculate x of 1.02 and so on. Okay. Fine. On a similar manner, you can try to work out how to do this with the trapezoidal method. We may not look at it, we may not do it, but then it is kind of similar to the implicit Euler method. Okay, so try working out the trapezoidal method, maybe just for 1 or 2 time steps. Okay, and then that should be kind of helpful. Next, what we have is the establishing the order of accuracy for the trapezoidal method, that it is second order accurate. And then we will proceed to look at the stability analysis for these solution methods. Okay, so that is what is coming up next, establishing order of accuracy for trapezoidal method, and then stability of the methods. Okay, so that is what we will take up in the next lecture. Okay, so if you have any questions, you can ask me. Otherwise, I'm going to stop here and then talk to you on Monday. Okay, so I may post your next assignment on the basics of finite difference method. Okay, because we have I think 2 or 3 more assignments, so I'll kind of inform you that. Okay, fine. Any questions, anybody?
Sir, just want to share the update from our batch
Yeah.
students regarding the means everyone agreed to go with means 2 pages sheets from our
Okay.
batch. Yeah,
Sure,
I think
sure.
I think Arunachalam batch also, like senior batch also, they have also agreed for the, I think 1 sheet page. I think we can go with that approach.
Okay, fine. So 2 pages means front and back of 1 sheet, or 4 one-sided?
Sir,
Ah.
sir, only 2 pages, sir. Either front and back or single
Sure, sure.
side.
Sure.
That's
So
it, sir.
essentially it is both sides of a single A4 sheet.
Yes, sir. Yes, sir. That's
Fine,
it. Sir.
fine.
Yeah, that,
Yeah,
yes, sir. Yeah.
Yeah. And I'm actually fine even if you bring 4 sheets, so not a problem, but maybe the code office may not be fine with it. Okay, fine. All right, that is good. So we will stick to this both for the midterm as well as the final exam.
Yes, sir. Yes, sir.
Final exam,
Final-
maybe we can reconnect, sir, on that,
Okay.
because I think the portions will be more.
More,
We can
yeah.
maybe we can
We can
Sir,
have
means
more
we can-
sheets. Fine.
Sir, from our batch, close book, close notes only, sir. We will have a 2-sheet formula sheet. We don't want any
Sure.
open books.
Sure. We'll go with closed book exam for the midterm and also for the final. We'll see. For the midterm, you will stick to bringing some 2-page, 1-page sheet, whatever, and then stick to that.
Okay.
Yeah.
Sir, sir, one suggestion, one obligation, sir. Whatever the assignment you are going to give, the due date, you can give me after 22nd or 23rd, sir, because we have exam on 8th and also 16th. We are preparing.
Sure. Yeah. No, the thing is, it may not be after 22nd because then we will have no time to do the next assignment. I'll try to put it a little longer, but I don't think it will take a lot of time for you. Okay.
Okay. Okay.
Yeah, because the toughest was the solution to system of linear equations was the toughest. Next ones are kind of straightforward. So if you spend probably a few hours, you should be able to solve it. Okay.
Okay, sir.
Yeah. I may not extend it too long because we have to do at least one more tutorial, 1 more assignment or 2 more assignments I have to check. So
Right, sir.
because of that, but you should be able to do it quickly. Should be
Okay.
fine. Yeah.
Thank you, sir.
Yeah. Okay.
Thank you.
Anything else? Anybody? No. Okay. Thank you, everyone. I'll talk to you next week on Monday.
Sure. Thank you, sir. Thank you.
Thank
Thank you,
you.
sir.
Thank you. Thank you. Bye-bye.
Thank you, sir.
Thank you. Bye.